Я рада представить нашу гостью Тамару Мчедлидзе, которая сделала PhD в университете Афин. Да? Сейчас она работает в Карлсруhe университете. Она занимается вопросами укладки графов, визуализации графов, как с теоретической, так и с практической точки зрения, включая в себя экспериментальные исследования. Сегодня она расскажет про Upward Book Embedding of ST Graphs.
Спасибо, Лен. Добрый вечер. Спасибо, Лене, за введение. Доклад я буду вести на английском, потому что сегодня, в общем-то, первый раз, когда я докладываю в русскоязычном университете. Для меня это такое особенное знаменательное событие, потому что я уехала из Грузии в 2000 году и с тех пор, в общем-то, никогда не презентировала ничего на русском языке. Так что для меня это вот, как бы, было бы довольно трудоемко презентировать сегодня на русском, потому я буду презентировать на английском. Но вот хотела сказать, что тот факт, что я в русскоязычном университете и буду говорить по-английски, вызывает у меня некий такой дискомфорт, потому хочу признаться, что так, слегка нервничаю. Вот. So, I switch to English, and I will be talking about upward book embeddings of ST digraphs. So this work started on a workshop a year ago, or a bit more, and the work was done with Italian colleagues from University of Perugia and University of Roma Tre, both in Italy. So I'll start with defining the problem. The object of our study are so-called digraphs. So these are directed graphs without cycles. Not only, they are additionally upward planar. Upward planar means that we can draw these digraphs on the plane such that all the edges are curves monotonically increasing in the upward direction, as you see here, and additionally they do not intersect each other. Yeah? So upward in natural sense. So all edges are curved monotonically increasing in the upward direction. So given an upward planar digraph, we want to construct an upward book embedding of it. And what is an upward book embedding? An upward book embedding consists of two items. So the first item is the ordering of the vertices, which we place on a vertical line and call this vertical line a spine. The ordering is such that it's actually, if you know, a topological ordering of the directed graph, or more precisely, it is such that every edge has its source numbered with a number smaller than its sink. So every edge also points up in this spine. So this is the first ingredient of upward book embedding. The second ingredient is assignment of the edges to one of the K sets. Yeah? Here we have two sets, one on the left half plane, one on the right half plane. So these half planes we call pages. Yeah? And then the requirement is that no two edges on a page intersect. So it means that no two edges are allowed to have their endpoints alternating. So something like this is not allowed. And graphically we represent those edges in the pages as semicircles, yeah? But this doesn't matter. Okay, so this is so-called upward book embedding. Here you see an upward book embedding with the two pages, and this is the spine. Of course, you can imagine that there could be more half planes which have as a boundary the spine, and then you can talk about K-page upward book embedding. Yeah? And we abbreviate those as tube or cube. So the main open problem which have been popularized by Nowakowski and Parker back in 1989 is whether the page number upward, so the page number, let me go back, something that I didn't say. So the minimum number of pages that you need in order to construct an upward book embedding is called the page number, upward page number of an upward planar diagraph. Yeah? So the minimum number of pages you need for an upward book embedding is the upward page number. So the question whether the upward page number of upward planar diagrams is bounded is open. So we don't know that. In this work, we studied the question which upward planar diagrams have a two-page upward book embedding, and whether given an upward planar diagram, we can decide whether it has a two-page upward book embedding. So shortly, we study the following question, which has been popular since 17th century. Okay, so before I proceed with the results, I would like to introduce some related work. And the first slide on related work is about upper and lower bounds. So how many, what is the page number on the page number of upward planar graphs? So I'm not talking about undirected graphs. As you understand, page number can also be defined for undirected graphs, but I'm not touching them here. So for directed trees and unicyclic graphs, the graphs with a single underlying undirected cycle, the page number is 1. For series parallel graphs, the page number is 2. If you haven't heard about series parallel graphs, these are graphs that we can recursively construct by series and parallel composition, starting just with a directed edge. N-free upward planar diagrams have page number 2, and N-free are those which don't contain this subgraph, this graph as a subgraph. Other classes of upward planar graphs have been studied by Fradi and others. In particular, they have shown that if the largest four-connected subgraph, four-connected component of a graph has size k, then the page number is bounded by minimum of these two. And in case the diameter is bounded, then the page number is also kind of sublinear. One of the results in this work that I'm going to talk about is that planar ST graphs with large faces have page number 2, and the large faces, like the definition of large faces, are those which have don't have transitive edges. So in this graph, we don't have transitive edges, and the right side of every face has at least 3 edges. I'm going to talk about this more. So planar ST diagram, for planar ST diagram, lower bound of 3 was known by Novakovsky and Parker. This is the lower bound. It has page number 3. And another example of lower bound of 4 has been provided by Hung. And for a cyclic planar graph, we know that the lower bound is quite large. It's n over 2. Yeah? But a cyclic planar graph are not upward planar. Yeah? These are more general graphs. So this is an example of a graph representing lower bound. And you can see that this graph is not upward planar. In particular, there is no way to place this edge in order to make it monotone, yeah? And non-crossing the other edges. So this second slide on the related work is about the decision problem. Yeah? So given an upward planar graph and the particular number of pages, how expensive it is to decide. And for a cyclic diagram, and 6 pages, it was known that the problem is NP-complete. What we have shown in this work, that for a cyclic diagram and 3 pages, the problem remains NP-complete, but I'm not going to talk about this result here. For a cyclic diagram and 1 page, the problem can be decided in linear time. For outer planar ST diagram and triangulated ST diagram and 2 pages in linear time. For planar ST diagram of width W, so the width W means that the maximum number of mutually independent vertices is bounded by W. For such graphs, we can decide in this time complexity. So this was work with my advisor during my PhD. And ST diagraph with small faces Yeah, for ST diagraph with small faces, we can decide in linear time. I'm going to talk about that. These are the small faces. I will define them. And for ST diagraph of branch with beta, whatever that means, for this diagraph we can decide in this time as well, and I'm going to talk about this result later. Okay, so I start about with the existential result for planar ST diagraph with large faces, and I have the numbers here, theorem 7. Yes, so I leave the original numbers which are happening to be in the paper so that you can refer to the corresponding theorem. Okay, so I am going to prove the following theorem. Let G be a planar ST graph with no transitive edges such that the right part of every internal face has at least 3 edges. Yeah, so we don't have transitive edges, and the right part of every face contains at least 3 edges. Yeah. So something that I didn't mention, the ST graph is an upward planar graph with a single source and single sink. Okay, so for this class of graphs, we show that G always admits an embedding preserving 2-page upward book embedding. I also have to specify what means embedding preserving. It means that if my original graph is given with some embedding, then the 2-page upward book embedding is going to preserve it. So the faces are preserved. The ordering of the edges around every vertex is preserved. This is another interpretation of that. So, okay. So this is our ST diagraph. This is our ST diagraph, and yeah, I have to introduce a tool which is called Hamiltonian embedding preserving Hamiltonian completion. This is quite intuitive. So let's look at an ST diagraph and a 2-page upward book embedding. If we look at the consecutive vertices, some of them are connected by the edges of the graph, some of them are not. So what I'm doing here, I'm connecting the vertices which are not connected by edges of the graph by these dashed edges. Yeah. So now I'm going back to the original planar embedding of my graph, and I'm inserting those edges. And what I see that they apparently live inside the faces. So this kind of is an indication of the following fact, that a planar ST graph has a 2-page upward book embedding if and only if it admits an embedding preserving Hamiltonian completion. So Hamiltonian completion here are additional edges which I add, directed edges which I add, but only within the faces, such that the resulting ST diagraph remains, so it remains a cyclic planar, single source, single sink, and has a Hamiltonian path from S to T. Yeah, so these two conditions are equivalent. This has been shown in one of the previous works. So I'm using this fact. From now on, I'm not going to search for book embedding, for 2-page book embedding, but I'm going to search for Hamiltonian completion for this result. Okay, so this is an ST diagraph. I need another tool, which is called a dual. You probably all know the notion of dual for undirected graphs. In directed graph, the difference is that I have 2 vertices associated with the outer face, and one corresponds to the left boundary, one corresponds to the right boundary. And the dual edges, so every edge has its dual edge connecting the 2 incident faces. The dual edges are also directed, and the direction is always from the left face to the right face. Yeah, for instance, this edge is directed from the left face to the right face of this edge. So if initial upward planar diagraph is ST diagraph, then the dual is as well. This is a known fact. What we can do, we can construct a topological ordering of this dual graph. Topological ordering as already defined. So this is an ordering such that every edge has its source numbered smaller than its sink. So this is a topological ordering. You see the numbers, and when I associate numbers with the vertices of the dual, it's like I number the faces of the original graph. Yeah? So therefore, I can define the following subgraph gi of G, which is composed by the first I faces. Yeah? So I take the first I faces. For instance, this is G3. Yeah? The first 3 faces, like 1 is like incomplete in a way, but it doesn't matter. 2 and 3 are here. So this is Gi. And Si and Ti are the source and the sink of the ith phase. Okay, so Si and Ti, source and sink of ith phase. Okay, so the proof is by induction in the topological ordering of the dual. So I'm going to add phases one by one, and I'm going to show that I can augment my Hamiltonian completion. So I'm not discussing the base case, it's quite simple. But I'm assuming that by induction hypothesis, we have that Gi minus 1 contains a Hamiltonian completion. And I'm going to distinguish how this Hamiltonian completion looks like. Based on whether it visits the edge just before the source of the next phase and just after the sink of the next phase. So the next phase is going to connect the Si to Ti, yeah? And I'm distinguished based on these edges. So in the first case, I have that both edges are visited. Since both edges are visited, so both edges are visited. Okay, good. And in my construction, I'm going to preserve the following invariant. For 2 consecutive edges of the right boundary of G, at least one belongs to the Hamiltonian path. So it can be no 2 consecutive edges on the boundary so that none of them is visited, yeah? In other words. So this means that if this vertex and this edge and that edge is visited, this edge and that edge may not be visited, yeah? But this edge and that edge cannot be consecutive, right? Because otherwise the invariant is broken. So there will be one edge inside here which is visited, yeah? Maybe even the first edge, but at least one inside on the left boundary of my next phase is going to be visited. So the second case, I have that one of these is visited. So here I have that without loss of generality, I assume that the bottom is visited and top is not visited. Since top is not visited, then the one before T is visited. And in the last case, none of them are visited, neither this nor that. Therefore, I have that this and that are visited, and I know that this edge and that edge are not the same edges. Yeah, neither they are. Yeah, they are not the same edges because I don't have a transitive edge in my graph. Okay, good. So now I'm going to create the new phase, which is Fi, here with source Si and sink Ti, and I'm going to augment my Hamiltonian completion. So I use this edge, yeah, to bypass. I bypass this edge and construct a path like this, from this vertex like this. And you can see that since this edge was visited, not visiting that is fine with the invariant. And the same here, yeah, this visited, not visiting that is fine. Similarly here I have this edge which is visited, so I can use it to bypass my phase. And here the invariant still holds. Here it again holds. In the last case, a little bit different. In the last case, I do 2 bypasses. Yeah. The first edge is used to bypass kind of first segment of the phase. It doesn't matter really until where. And this edge is used to bypass the second part of the phase. But what is very essential here that this path contains at least 3 edges. That was the condition. If it's not, then we cannot preserve the invariant. So here you observe that only because we are doing this bypass, our invariant holds. So this edge is visited, this is not visited, this is not visited, this is visited. Yeah? So we have that invariant really holds. So this technique cannot be extended to like more general phases. So this was the proof of the fact that every graph with large faces has always two-page upward book embedding. And now I'm going to switch to small faces, yeah, which is like the other extreme. Okay, so the other extreme contains only small faces in the sense that it either contains faces like that, where at every side we have a path of length 2, or these are so-called generalized triangle, where you have a transitive edge on one side and like a path of arbitrary length on the other side. And the theorem I'm going to prove is the following: that let G be a plane as the graph where every inner face is either a generalized triangle or a rhombus. Then it can be decided in linear time whether this graph admits an embedding preserving two-page upward book embedding. Yeah, so this is like counterpart of the previous result. For large faces, embedding always exists. For small faces, we can decide. Okay, so the proof more or less is a consequence of all the results. I'm going to quickly go through it. So if you look, this is an example of such a graph with small faces. You have only generalized triangle and rhombuses. So what I did here, I inserted these additional edges within the rhombuses. Yeah? And it is true that every Hamiltonian completion of that has to use all of those edges. And the only thing the Hamiltonian completion kind of can decide is how these edges are oriented. So this gives us such a mixed graph. A mixed graph in the sense that we have both directed and undirected edges. So V is the vertex set of the original graph, E are the original edges, EU are the undirected edges which I have inserted in the face. So I recall my Hamiltonian completion lemma, which says that, yeah, there is a two-page book embedding if and only if there is a Hamiltonian completion. What I also observed that any orientation of these undirected edges keep the graph acyclic. Yeah, you can easily see that by orienting edges one by one. Whenever you orient one of the edges and just ignore all the other undirected edges, you keep the graph acyclic. So the graph stays acyclic. This actually means that this mixed graph is going to have an Hamiltonian orientation if and only if it has a unilateral orientation. Yeah? And unilateral means that it has an orientation such that each pair of vertices is connected by a directed path. Yeah? So the whole thing boils down to deciding whether this mixed graph has a unilateral orientation, which is very funny, but this is our old result. So at some point I thought that this problem is relevant to this mixed orientation, but it wasn't clear for me how big cases we can resolve back then. Yeah, so there is an algorithm which in linear time in the size of the graph decides whether a mixed graph has a unilateral orientation. So we can use that in order to decide whether there exists a Hamiltonian completion and in order to decide whether there exists a two-page upward book embedding. So this is what happens with these small faces. Yep. So maybe you have questions until now, because I'm switching to the main part of the talk about the graph of bounded branch width. Okay, whenever you have questions, just interrupt me. So, graphs of bounded branch width, Vita. For them, we can decide in this time whether there exists a two-page upward book embedding, and in particular, this means that the problem is fixed parameter tractable in the branch width. Okay, so this is theorem 18, and that's what it says. So it can be decided in the following time whether an n-vertex embedded planar ST graph of branch width beta admits an embedding preserving two-page book embedding. So I have an embedded and embedding preserving here in parentheses because you can remove both. Yeah. So if the initial graph is embedded, then you can ask for embedding preserving two-page upward book embedding. If it's not, then yeah, not. So we can decide both in both situations.
I'm not sure everyone understands the term branch width.
Embedding?
Branch width.
Branch width. I'm going to define.
Okay.
Yeah. I'm going to define the notion of branch width. So branch width is a parameter of the graph. Okay, so before I come to defining branch width, so at the moment I need it, I'm going to define it. But before that, I'm going to talk about the main idea. So the main idea is the following. So you look at this two-page upward book embedding, and you observe the following. What is actually important for augmenting it further? So assume that this is only part of the graph. And what is important for augmenting it further? It is important how the spine is visible from outside. And here you observe that spine is visible just incident to the source, just incident to the sink, and from this side the spine is not visible at all. So you can abstractly denote this embedding by the following type. Yeah, so you have the red is always on the right and blue is always on the left. So that's the convention to help the perception a little bit. So here we have visibility, here we have visibility, and no other visibility. And these are all the possible types. Yeah, according to that. For instance, if you look at that, it means that from the right side there is no visibility close to the source, no visibility close to the sink, but there is a visibility somewhere in the middle. Yeah. So when we don't have visibility on the sides, we are interested whether there exists at least some piece somewhere in the middle where the spine is visible. Yeah. So according to that, you can categorize all the embedding types, all the two-page upward book embedding types. There are many, but you can observe some similarities, some symmetry. So this is symmetrical to that. You can flip it, and there's also some symmetry, horizontal symmetry here. Okay, so why do we need actually this type? This type helps us to prove the following substitution result. So let's take an ST diagraph in a very abstract form. And imagine it's two-page upward book embedding. And let's assume that this graph is not tri-connected, so it has a separating pair. So it has a pair of vertices S prime to prime, such that when we cut at those vertices, we disconnect it. Yeah? So this is like a cut pair. And let's look how this graph looks like here. Yeah? And at its surrounding. So this subgraph G prime is going to have some type. Yeah, the embedding, the two-page book embedding here is going to have some type. And apparently what happens is that if I take a different two-page book embedding, let's say now of a green color, yeah, of this subgraph, which has the same type, I can plug these things together again. So what actually it says that I really don't care how the edges of the G prime are arranged on the spine here and there, and what is the actual distribution of edges to the pages. If the type is the same, I can plug back the result. So which means that only the type is important. Yeah, so I don't need all of different to be able kind of to plug the sub embeddings together. I don't need to store different embeddings, but I need to store just one embedding of each type. So this is the actual substitution lemma. It just says what I have just explained on the picture. Yeah, I'm not going to read it. Okay, so you have seen that in a way we can decompose the graph along cut vertices and then kind of build it up together. There exists a data structure which is called Spqr Tree. Have you heard about it? No? Nobody? Nobody heard about it? It's a very nice data structure which models a decomposition of a graph down to 3 connected components. So it models how graph is decomposed along cut pairs. Yes, I'm not going to define it formally. I think it's easier to understand it just by example. So we take this graph and then we remove one edge. Yeah, here we remove the edge 114 between source and sink. This is like general biconnected graph. Yeah, this is a biconnected graph, and we take one edge and remove it, and we start modeling with that edge. So the first node of our tree, of Spqr tree, is this 114. Yeah, the node corresponds to an edge. And now the remaining graph, yeah, has some cut pairs, and we look at the maximal cut pairs. For instance, 1 and 6 is interesting to us, but 3, 4 is not interesting because 1, 6 is going to include 3, 4. So we find the maximal cut pairs and find which subgraphs are removed using those cut pairs. Yeah? And you see that here 1, 6 is 1, 6 is one cut pair, and the graph between them is represented in the next node as a dashed edge, so-called virtual edge. And 2, 14 is another cut pair, and it is represented as another dashed edge. Yeah? All the other edges are the real edges of the graph. And this is so-called skeleton of that node, and you also see this letter R here, which means that if I connect the poles of this graph by an edge, then I obtain a tri-connected graph. So R components correspond to tri-connected components in the graph. So now I continue this decomposition further, and here I see that my R component, my R node has 2 S nodes. One of the S nodes corresponds to this part. You see 1, 3, 3, 5, 5, 6, 1, 3, 3, 5, 5, 6, where 3, 5 is a virtual edge. It corresponds to this component. Yeah? And this node has a letter S in it because it is a series composition. It's a series composition of edges and components. Yeah? So this series has again another child. It has 3 children actually, 2 of them corresponding to edges, which become leaves. They don't extend further. So in general, the leaves of the decomposition are the edges of the graph. And this subgraph here corresponds to a P node. It looks like that. Its skeleton looks like that. And this P node consists of why it's P, because it's a parallel composition. Yeah? Parallel composition of 3, 5, and the path 3, 4, 4, 5. Yeah? Yeah. And this 3, 4, 4, 5 is again a series composition of 3, 4, and 4, 5. And so on. So overall, it's a tree where every node is either an edge, yeah, and then it is a leaf, or it is S, P, or R node. And Q stands for the leaves. So these leaf edge nodes are called Q. That's why it is S, P, Q, R. Okay, so now we have the Spqr tree. And what is it useful for? Yeah, before we go on, let me define something else. If we look at this node, yeah, we can define so-called pertinent graph of that node and denote it by pert of mu. Yeah, this is mu and this is pert of mu. And the pertinent graph is everything which hangs below. So I take the skeleton and I start going down and I glue all the subgraphs which are here. So in this picture, it is this subgraph, yeah, kind of subgraph which is represented by the subtree below here. Yeah, so this is pertinent graph. This is going to be used later. So an Spqr tree of a graph with n nodes can be actually computed in linear time. Proven by several researchers, but one of the results is by De Battista and Tomasia in 1996. Okay, so assuming that we have an Spqr tree, we can do kind of dynamic programming. Not kind of, but dynamic programming. If you remember the type, yeah, and the type of an edge, as you understand, can be either this or that. Yeah, an edge can either be on the left page or on the right page. It cannot do anything else. So every edge has only 2 types. Therefore, we can initialize the leaves of our Spqr tree. Yeah, we can say that leaves of our Spqr tree have these possible types. And then we can start promoting the possible types up in the tree. Yeah, so for instance, for these series nodes, we can compose all possible types here and obtain these types. Yeah, so this path can look like this, it can look like this, it can look like this, or it can look like this. Yeah, this series composition, and so on. We go up. So this dynamic programming at every node stores all possible types that this pertinent graph below can realize. Pertinent graph of that node can realize these edges. Okay, so I'm now going to talk about every type of node separately. So I have the P nodes, S nodes, and R nodes. Yeah, and I start with the P nodes. So let's look what happens at the P node. And just to help a little bit the intuition, I start only with 2 components. Yeah, so 2 components are glued in parallel, which means that the source and sink of both components are identified. And just as an example, imagine we have G1 and G2. G1 may have these types, G2 may have these types, yeah, which have been stored by dynamic programming until now. And observe that if I take this type and that type, I can create this type. Yeah, so take this and put it on that side. Yeah, so they are compatible. I can do 2 pieces of puzzle that I can match. Or this type and that type make again the same type. Yeah, so I can make as many times as possible as I want this kind of S thing. Okay, this is in case of 2 components, and in general I have more. And not only I have many components, but I also have the freedom to permute them. Yeah? If my embedding is not fixed, then I even have the freedom to permute these components. And so a 2-page book embedding of these components, for instance, could look like that. Yeah? So I'm now going to discuss a very particular type. And the question is of how to reorder the components and how to decide which existing types of the smaller components make me a particular type of the larger component. Yeah? So we have kind of puzzle game, but we also have to choose. And so for each puzzle piece, we have many possibilities, yeah, which exist. Yeah? Many but bounded number. So in order to decide whether there exists an assignment of types to the components, so they already have types, and an ordering of them which realize the particular type, yeah, we create this flow network. And the flow network is composed as follows. It has a source and a sink. The source is connected to 5 nodes. Here the 5 nodes exactly correspond to the 5 parallel components. So we have as many nodes in this network as the components here. Then we have a row of the types that are realized by these components. So by our dynamic programming, we have all the types which are realized by these components, yeah, and they are all together these ones. And then we have the arrows going from the components to the types, which means that component realizes this type. Yeah? So this is kind of always changed. Yeah? So we have to construct this network every time we make this decision. And then we have a construction here which give us the constraints. So one of the ways this type can be realized is this, which means I have this type, then I have this type, and then I have as many as I want of this type, and then maybe one of this type. Yeah, and this is exactly modeled here by these waves. So I can have this type and this type at most once, each of them, and together they are at most 2. Then I have as many as I want of this type. This is modeled by the weight, by the lower bound 0 and upper bound infinity. Then I can have at most 1 of this type and as many as I want of this type, and altogether they are at least 1. Yeah? They have to be at least 1 to create this hidden thing on the close to the source on that side. Yeah, so this is a flow network, and what happens now is that a two-page upward book embedding of this type exists if and only if this flow network has a feasible flow of value k. Yeah, where k is the number of parallel components. And yeah, this is, we have lower and upper bounds here, and we have only the feasible flow question. We can reduce it to the maximum flow problem with capacitated edges and just solve it by standard Fortin-Fulkerson algorithm in this time, where f is the value of maximum flow and is the size of the network. Yeah. Okay, so n is the size of the network, and this upper bounded by the number of parallel components. So we have k here, and we have k here as well. So we get the following lemma: let M be a p-node with k children. The types realizable by pertinent graph of M can be computed in k squared time. So this is about the parallel components. I'm going to talk a little bit about the series component, but in series composition, but it is much simpler. So let's assume we have some kind of series composition, let's say of 3 components, and let's say this component realizes this type as one of the possible types, and this realizes this type, and this realizes that type. So I insist that since it realizes these types, it also realizes this altogether graph, yeah, the combined graph realizes this type. And how do I see that? So I guess a type here, and then I start checking. So I check what happens here above, yeah? And if there is no visibility, then I know that here should be no visibility. Then I check what happens here below. There is no visibility, there should be no visibility here. And then I check what happens in the middle, yeah? And in the middle here means in one of the middle components from the right, visibility from the right, or in the topmost or bottommost component next to the source here and next to the sink here. So it happens to have visibility here, so there is a visible piece from the right. That's what happens for a series composition. So we can, for every type, we can quickly check whether this type is realizable. So therefore, the types realizable by pertinent graph can be computed in actually constant time, yeah, because number of types is constant. Okay, good. So what we have just said, that for parallel and series composition, we know how to compute types of the pertinent graph. But the problem is that we also have the R nodes. Yeah? So we have the tri-connected components. So what to do with those? The Spqr tree doesn't give us any chance for that. It just leaves them as they are. So we need a different kind of decomposition in order to decide for 3 connected graphs. And here we are. Here we have the tool which is called sphere cut decomposition. This is another very beautiful decomposition of graphs. I'm going to define it. So a sphere cut decomposition is based on branch decomposition. So I'm first defining the branch decomposition. The branch decomposition is composed of a ternary tree, T, and a bijection between the leaves of this tree, yeah, and the edges of the graph. Yeah? So here we have, I think, 9 plus 5, 14 edges, and here we have 14 leaves. Now, I need to introduce some notation. So for every edge of this tree, when I remove it, I get 2 subtrees. Let's say edge is A, and I get TA, and the remaining vertices are TB. So now the edges of the graph which correspond to these leaves are called GA, and corresponding to those are called GB. And the vertices which lie in the middle, kind of which lie in the both, are called a middle set. So the width of branch decomposition is the maximum size of the middle set over all arcs of the decomposition tree. Yes, you go over all the edges of the decomposition tree, you look at the middle set and you take the maximum. And this is the width of the decomposition, of the particular decomposition. So now an optimal branch decomposition is the one which has the minimum width. Yeah, minimum width over all possible decomposition. And this number is called branch width of the graph, yeah, and denoted by beta. So a sphere cut decomposition is something built on top of a branch decomposition, is a branch decomposition together with a set of closed curves. Yeah, here the closed curve is exactly this one. So every subgraph, yeah, decomposed by an edge has a curve which bounds a connected subgraph, passes exactly through the middle set. Now I'm talking about the blue curve, yeah. Passes exactly through the middle set and it can pass at most one time through each face. Yeah, so it's not allowed to enter phase twice. So this is so-called news, but we don't need this term. So sphere cut decomposition and branch decomposition given together with such kind of curve. So here this curve is around GA, but I also draw the curve around GB for visual simplicity. Okay, so a sphere cut decomposition, given a G-connected graph of branch with beta and no vertex of degree 1, we can compute a sphere cut decomposition of the same width in cubic time. Okay, so this is a result of Dorn and others from 2010. Okay, so now we are going to use this branch decomposition to talk about tri-connected components. So unfortunately, the branch decomposition does not decompose graphs very nicely. So if you look at the two parts separated by a single step of branch of sphere cut decomposition, then the boundary, this middle set, is kind of large. And we have to do some tricks in order to implement the same idea with types. So I'm going first to explain what the tricks are, and then you will understand how it works. So first we do the following. So we look at these two subgraphs and we only take their boundaries. Yes? So I have removed the internal vertices. And additionally, what we do is that for every, there is an edge missing here. And then the next step, what we do, we look at directed paths on that boundary and we substitute them by edges. Every directed path on that boundary is substituted by an edge. And as the next step, we take each of these edges and we subdivide them twice. So why this complicated construction? First of all, we don't care about internal vertices when we plug the two components together. So we only care about the vertices on the interface, on the boundary. Yeah, that's why we have removed the internal components. Second, what we know is that each of these paths, however many vertices it's going to have, it's not going to intersect the spine more than twice. So if there exists a two-page upward book embedding where each of these monotone paths intersects the spine more than twice, then there is another one where it intersects at most twice. That's why we do this modeling. So we substitute every directed path by a path of length 2, actually, of length 3, like 3 edges, yeah? Because it may intersect the spine at these vertices, may not. So this is kind of enough for storing all the information. Okay, so we do it for all the edges. And here we have to do a bit more than before. So if before we had only the type and our type was composed only by how the edges are arranged on the boundary. Here we need to store a little bit more, because we see that we have many common vertices here, and when we decide whether these two pieces, the embeddings of these two pieces are compatible, we also need to have the ordering of these common vertices. So this new type is called outer shape pair of a graph. Yeah, this outer shape pair of the graph is composed of an ordering of the end vertices of the paths. Yeah, so these vertices, the vertices of the actual paths, yeah, that have length 3 in our modeling, and a tuple which give me the type of path pi. So for every path, I store a type. Yeah? So I have for each possible assignments of types to the path, and all possible orderings of the vertices that can be realized, I have such an outer shape pair. Yeah? So a type of a path is something very similar to type of a graph that I had before. Yeah, so it actually says how this path looks like. Yeah, it looks like this, or like that, or like this, or like that. And what actually happens is that all outer shape pairs of the graph can be computed from all outer shape pairs of GA and GB in this time. Yeah, and let me a little bit argue why this happens. So the size of the boundary here is bounded by a function of linear function of beta. Yeah, because the branch width of my graph is beta. Yeah, so this interface is beta. Now, what I can do for the graph, for the whole graph GA, I can guess an ordering, and I can guess an assignment of the edges to the pages, and these are beta factorial. Yeah? For each of those, I can create a sub-embedding of one graph and sub-embedding of another graph, and I can check recursively. Yeah, from my dynamic programming, I can check whether this subgraph and that subgraph has the corresponding outer shape pair. Yeah, and if yes, then I can say, yeah, this type exists for the whole graph. Yeah, so here we have beta factorial, the orderings of the vertices, and 2 to the beta assignments of the edges to the pages. So this is more or less which makes the time complexity of this decision. So this is only for a single step of composition. Yeah, and now you can imagine you can do dynamic programming on this sphere-cut decomposition tree, yeah, by storing this information and promoting it up and up. And what I would like to mention, there should be an H here, it's missing. What I would like to mention is that the edges of these 3 connected components are not exactly edges, right? The edge, like from this to this vertex, may be a whole component initially, yeah? A whole tri-connected component, for instance. Yeah? And then, in order to initialize the type of this edge, we use information from the dynamic programming on the Spqr tree. So this is corresponding to some node, possibly in Spqr tree. Some information has been obtained bottom up, and this information is then transferred to the dynamic programming on the sphere-cut decomposition. So now, taking all together, if we are talking about a single M node, R node mu with k children and branch with beta, the set of type realizable by the corresponding pertinent graph can be computed in the following time, yeah, times k, because k is the number of children in the Spqr tree, means that this is the number of leaves in the sphere-cut decomposition tree, and therefore it bounds the number of operations we do. Okay, so now I remind you everything. For P node, we have k square time complexity. For S node, we have a constant time decision algorithm. For R node, this is the decision. And additionally, we have that sphere cut decomposition can be computed in a cubic time, which overall results in this complexity which has been claimed in our theorem. So there exists an algorithm of complexity 2 to the O beta log beta n plus n cube time to decide whether an n-vertex planar ST diagraph of branch with beta admits a 2-page upward book embedding. So here is, I finished with the branch with result, and I want to wrap up a little bit. So what I have shown that for planar graph branch with beta and for ST graphs with small faces, the tuba can be decided in polynomial time, that for ST graph with large faces, tuba always exists. And the result that I haven't talked about is the NP hardness for digraphs, for directed cyclic graphs, and 3 pages. The problems which remain open. So complexity of deciding 2-page upward book embedding for upward plane graphs remains open. So whether we have this fixed parameter tractable algorithm, but we still don't know what happens in general case. We don't know whether the problem is hard or not. Complexity of deciding 3-page upward book embedding is also open, yeah, for upward planar digraphs, because our NP hardness proof uses graphs which are not upward planar. They are planar acyclic, but they are not upward planar. And the big problem which remains open is whether the page number of upward planar digraphs is bounded. So, thank you very much. Yeah.
По-русски?
Можно по-русски, как удобно.
Хорошо, а как планарный граф вообще хранится?
Как планарный граф?
So how planar graph is stored on your computer? So you have to not only, I think, store edges, vertex edges, but also faces.
The embedding. Usually the embedding is stored in a set of lists. So you have a set of faces. Yeah, all the edges are stored in the ordering in which they are traversed around every face, and for each edge you store this so-called doubly connected edge list, and for every edge you store the face on the left and face on the right, and this gives you enough information to traverse the planar graph, traverse it from face to face, and to construct the dual. And
okay, and so linear time is linear in number of vertices.
Yeah.
So not in the number of the whole information.
No, in the number of vertices always.
Еще вопросы?
So what is ST graphs different from other types that you chose? Them are they much simpler to construct all the embeddings, or are they some theoretical results that do not hold for other types?
ST graphs.
Why
ST?
Может по-русски, а? Потому что я не очень поняла.
Какой большой плюс в ST-графах заставил вас их именно выбрать для исследования?
Почему мы изучаем именно ST графы?
Проще и лучше, чем для всех остальных?
Чем для upward planar. Для них вот этот вот, когда ты, when you construct this dual graph, you know that the dual graph is also a ST diagraph. So it gives you some more structure. And in general, the decision questions whether a graph with a single source and single sink has an upward planar drawing is easier than for general upward planar graphs. Yeah. So a little bit more structure.
Еще вопросы? Нет? Давайте еще раз поблагодарим.
Спасибо.
Спасибо.